So we're honored to invite Professor Xiaolong Han from CIMIS. He will talk about nearly geodesic surfaces are filling.
Okay, thank you very much. It's a great honor to speak here. Today, I'll talk about some surfaces in three manifold, and I will use a tool from dynamic system and differential geometry. And the most important point is for us to see the picture. So a hyperbolic manifold is a Riemannian manifold with constant sectional curvature -1. Okay, so some important properties we'll be using for hyperbolic manifold is that it has a contractible universal cover, so we use open unit ball to represent the universal cover. And for every loop that's not homotopically trivial, it's homotopic to a unique length minimizing loop, which is the closed geodesic. Okay? So both the uniqueness and the length minimizing property do not hold in the sphere case. Okay? And today we look at a property called filling. So filling just means you have a submanifold which is carefully positioned in your manifold so that it cuts the manifold into contractible components. Like on a hyperbolic surface, you can have a closed geodesic so that if you cut along the geodesic, then it destroys all topology and you only get balls. So this is an example from my friend Yu Hao Xue. So basically, you look at this red geodesic. So you can see that it actually goes through the surface in a careful way, so destroy the topology of the hyperbolic surface. So if you have a simple closed geodesic, you cut along simple closed geodesic, that's not going to be fitting, okay, because it itself is a topology that has not been destroyed. So to create a single geodesic that's fitting, you have to be careful. But there was a recent question coming from my postdoc mentor, Yunhui Wu and Yu Hao Xue. So they ask whether random closed geodesic on random surfaces of large genuses are fitting. Okay, so even if it's hard to construct, so it's not so easy to construct a single fitting geodesic. But if you look at the collection, the space of all closed geodesic, they have some intuition that maybe random closed geodesic should be fitting. Okay. So I really like this question, and this question definitely attracts attention of international mathematicians. So Taylor Sapir, they have results which are related to this question. So they kind of say a random geodesic on expanded surfaces would be fitting. Okay. So today's talk is about how this phenomenon generalized to surfaces in three manifold. Okay, so before we talk about hyperbolic three manifold, let me actually review geodesic on torus. So if you think about torus, so let's use this unit square. So this is a torus. So if you think about geodesic on this torus, right, it's parameterized by the slope. Now, look at the space of all geodesic. That's look at number from 0 to 1. And then most geodesic will be those irrational geodesic, right? Because irrational number are much more than rational number. And those irrational geodesic on torus will be dense. Okay? So you can say a random geodesic on a torus is dense, right? Because if you think about 0-1 interval, those irrational numbers are like generic. So there are three observations for geodesic on torus. That's kind of very remarkable. The first one is that a geodesic on torus is either dense or closed geodesic. So this is already false for hyperbolic surface. I'm gonna show you some picture. So what do we mean by dense? Dense means you take this geodesic on torus and you take the topological closure, and then actually it hits a larger group, right? Because the geodesic itself comes from taking a one-dimensional subgroup of R2, right? Take R in R2, and then you X on a tangent vector, you get this geodesic. And so this geodesic is an orbit of a Lie subgroup, okay? Because R2 is Lie group, so this R is Lie subgroup. And in general, there's no reason that look at the orbit of a subgroup, you take a topological closure, you get the largest group. In general, that's not true. But here it's true, okay? So, and the second observation is that random geodesic is fitting. Because if you cut along my dense geodesic, you actually destroy all the topology of my torus, right? So if you think about it, take the torus, you cut along the dense geodesic. What you get is something infinitely long but infinitely thin, but it's, that space is actually contractible. Okay, so you destroy the topology of the torus by cutting along this dense geodesic. So fitting is actually a random property on torus. Moreover, because my closed geodesic are represented by those rational numbers, and my dense geodesic are those irrational numbers, they have different slope, so they will transversally intersect. So a random geodesic on a torus will transversally intersect every closed geodesic on your surface. So we will talk about generalization of these three phenomena to surfaces in hyperbolic three manifold, which a priori looks very different. But somehow it's their Lie group structure, somehow deep inside, some interaction in their Lie group would generalize these three phenomena to a huge class of surfaces in hyperbolic three manifold. Okay. All right, so that's the goal today. And before I start to talk about surfaces in three manifold, let me also review geodesic on a hyperbolic surface. So you have dense geodesic come from ergodicity of geodesic flow. You also have closed geodesic, just like torus case, right? So if I draw a picture like this, you have a new phenomena, which is called lamination. So you can take this beta 1, beta 2, and then you draw a geodesic which cross them once. Now you can apply this construction called Dehn twist. So this is gamma and this is beta. So whenever you come near beta, you do this 360-degree twist and then you go. That's called Dehn twist. If you think about you do Dehn twist like infinite many times here and infinite many times here, then you get a geodesic lamination which has 4 geodesic, lambda 1, lambda 2, beta 1, beta 2. So it's 4 geodesics. But those lambda 1, lambda 2 are neither dense nor closed. Okay, so it's a geodesic that's different from geodesic on torus. So here, what's interesting is that this set is the kinetic but not path kinetic space. You probably learned this from topology class, which is topology sine curve. So here it's not path kinetic, but you're like limiting this geodesic. So you're limiting this geodesic. It's one kinetic space. And actually, if you look at the tangent line, so at every point, geodesic is smooth, so look at the tangent line. Okay? So that's a line bundle. The tangent line over this 4 lamination is a kinetic set. Okay? So basically, because this is my beta 2 is my closed geodesic, and my lamination here, the tangent line is like approaching this guy. So it's actually a kinetic set, even in the tangent line bundle. Okay? And also you have other phenomena like geodesic supporting on subsurface. So compare geodesic on a hyperbolic surface with geodesic on torus, we see a very big difference is that geodesic on hyperbolic surfaces, you have a huge variety. It's not so easy to classify. So it's very different. This is called flexible or wild. And so there's a reason for what happened. So look at this matrix, 2 by 2 matrix, we determine 1. So this guy is the isometry group of hyperbolic geometry, 2-dimensional hyperbolic geometry. So take the 2-dimensional hyperbolic space, okay, and its isometry group is this one. And this one admits so-called Kn decomposition. You probably have seen this or will learn this in a Lie group course. So K is the rotational group, and A is this geodesic, where it's a diagonal matrix, and N is this horocycle, so it has 1 in the diagonal and some entries in upper triangular entry. Okay, So if we compare these two matrices, what's the essential difference? The essential difference is that if you multiply this matrix many times, like let's say 100 times, and if you multiply this matrix 100 times, then the largest entries grow differently. Right? This one grows exponentially. This one grows polynomially, linearly. So if you think about this subgroup corresponds to this matrix, it moves on the surface in a much slower rate compared to this one. Because this one, it acts on a point and then moves exponentially fast. But this one moves polynomially. Okay? So if we do any math, what do we expect? Because this one moves much slower than this one. The expectation is that we might have more control. So we might have more control, more rigidity about this orbit. Okay? That's the expectation. And there was a theorem from around 90 years ago, which says horocycle flow on closed hyperbolic surface is minimum. So basically, this orbit on hyperbolic surface is always dense. Okay? So if you recall geodesic on hyperbolic surface, you have many different classification, many different type. But this orbit is always dense, just one type. Okay? That's called control, because you have a very good clean classification of objects. And horocycle on cusp surface is just like geodesic on torus, is either dense or close. Okay, so it's either dense or close. We see this phenomenon again, right? It's either dense or close. Okay. And if you are interested in topology or geometry, by control just means if you want your surface to sit somewhere in the space, let's say I want my surface to sit here or near here, the surface must be supported near that place. That's what I mean by control. Okay? And today we're going to talk about the so-called geodesic submanifold. So this generalized geodesic. So geodesic is one-dimensional guy. Okay? Geodesic locally is distance minimizing. It's one-dimensional. If you talk about surface, right? A surface is two-dimensional. It can also be a geodesic surface. So geometrically, there are many ways to define the geodesic submanifold. One is that it has principal curvature 0. Just like, so how do you define a curve to be geodesic? A geodesic is a curve with curvature 0. Okay? So it's like straight in space. A geodesic submanifold is like a submanifold but with principal curvature 0. So this is like the higher dimensional generalization of geodesic. And a geodesic plane is a two-dimensional analog of geodesic. Okay? So if you think about examples, take the Euclidean 3 space. So take the Euclidean 3 space. This Euclidean 2 space is a geodesic surface, okay, because it has curvature 0. But if you take the sphere, right, it's not geodesic because the curvature is not 0. Okay. So basically, a geodesic submanifold is one where if you walk on the surface, it feels the same as walking on the ambient space. But if you walk here, it feels very different from walking on Euclidean space. Okay? So geodesic submanifold are submanifold which looks very much like ambient manifold in terms of geometry. So we can ask the question, because geodesic on hyperbolic surfaces, you have so many types, it's very hard to classify them. What about this higher dimensional analog, right? So you go up one dimension. What do you expect? You will expect geodesic surfaces to be as flexible like geodesic on hyperbolic surfaces because they both have codimension 1, they both have curvature 0. Okay? What do you expect? So actually, it's either dense or close. So it's just like geodesic on torus. So when I first learned this theorem from a paper of Caligari Marcus, I was really shocked. And then I tried to think about whether I can do a project using this theorem. It's really beautiful. And actually, this is true even in higher dimensions. So you take a hyperbolic fine manifold and take a 3-dimensional hyperbolic space. You project to this hyperbolic fine manifold. So either it's a closed submanifold, just like closed surface, or it's going to be dense in a higher dimensional submanifold. So it's going to be dense in a 4 manifold or dense in a 5 manifold. So there will be never lamination because if you think about lamination, take a closure, it's not any submanifold. That's not a submanifold. Okay? So you see some rigidity. I'm going to explain briefly why we have this rigidity. So I first learned about this Ratner theorem from the paper of Caligari and Marcus Nevis. So 5 years ago, they initiated a new direction, which used Ratner theorem and homogeneous dynamics to study negative current manifold and minimal surfaces. And this is a very new direction, and they defined this minimal surface entropy. And they last year, so Marcus Nevis gave a new proof of mass rigidity using the invariant they defined. And I use this to give some topological application. So you're going to see that later. So the crucial difference between one-dimension geodesic and a higher dimensional geodesic submanifold is that for the higher dimensional geodesic submanifold, you have the inclusion of the unipotent orbit. Because previously I said this horocycle, this matrix 1, 1, so this matrix, so this guy, right, its orbit is always dense in your closed hyperbolic surface, so it's very rigid. So if you take a geodesic surface here, so this geodesic surface inside your hyperbolic free manifold, its universal cover is the H2. But H2 is actually the quotient of the isometric group of H2. Okay? Right, so whenever you have a group, you mod out by the compact, the maximum, like this compact subgroup, you get the geometry. Right? So geometry and the isometric group are closely related. But this guy is the SL to R, and this orbit lives in here. So basically, in 2-dimensional higher, you have this surface you see has this orbit living inside. That's why it gives you this rigidity that you don't see for geodesic. Okay? So even if they are geometrically the same, they have curvature 0, but it's because of inclusion of this orbit, which forces your surface to behave very rigidly. Okay? So previously, I described 3 properties of geodesic surface, of geodesic on torus. And we see that the first one, either dense or closed, generalized to geodesic surface in a closed hyperbolic manifold. So this is true. So by Ratner and Shai. Okay. And today the surface we study is called pi1 injective. So basically the surface, the fundamental group comes from the fundamental group of the manifold. So basically it comes from essential thing, right? So if you think about, take the Euclidean space. If you take a genus 2 surface, this is not pi1 injective because the Euclidean space have no pi1. That's not pi1 injective. Okay. So those surfaces come from the subgroup of the manifold. So for example, take the 3 torus, whose fundamental group is Z3, and take the horizontal Z2, that is pi1 injective. Okay. So every element in your pi1 comes from element of ambient pi1. And 2 surfaces are commensurable, so this notion is that my surface agree up to finite cover. So basically, after conjugation, so conjugation is like homotopy, then my surface, the fundamental group intersect into a finite index subgroup. So usually, lots of theorems in group theory or topology are stated up to finite cover because you have a group and you have finite index subgroup. We often say virtually something. So virtually something means the property hold for this finite index subgroup. So commensurable just means take surface 1, take surface 2, have a common finite cover. Okay? Because this finite cover give you a subgroup of finite index in both surfaces. Okay? That's commensurable. I don't want to distinguish between commensurable surfaces because commensurable surfaces, in your manifold, they look the same. So think about hyperbolic geodesic here. So this guy called gamma, this is geodesic, and gamma square you just wrap around twice. Okay, so geometrically they're the same, but just with different multiplicity. That's the commensurable. I don't want to distinguish such object because I only care about the support. I only care about where my surface sits. I don't care about what's the multiplicity of my surface. So I don't distinguish between commensurable surfaces. So take this genus, which is that in my commensurability class, take the smallest genus. So basically, it's the area of my surface. Okay, so it's like the area of my surface. My area of my surface is going to be 4 pi times g minus 1. So here, there are some foundational results due to Maclaurin Ray and Alan Ray. They construct infinite many arithmetic hyperbolic manifold that contains countably infinite many convertibility class of geodesic surfaces. So you have infinite many hyperbolic manifold, and each of which contains infinite many total geodesic surfaces. Okay? Because I'm going to say my theorem, I wish my theorem to hold for infinite many objects. All right, so that's some of the background. And the notion, which generalizes to 3 manifold, there are 2 notions. The first one is cofitting. So how do I define fitting for a surface? Because my surface is just homotopy class of surfaces. My surface is cofitting if my surface cuts every non-trivial loop in my manifold. Okay? So here, there are 2. So take any representative in my surface. Take any non-trivial loop. My surface is going to cut that. Okay? So if you think about the picture in the first slide, where I have a fitting geodesic on a hyperbolic surface, that is an example of a fitting homotopy class. Because no matter how you homotope the geodesic or not geodesic, they are going to intersect. Okay? So that's called fitting. This just means, okay, let's say your manifold has topology. So topology just comes from pi 1 because my manifold is aspherical. It doesn't have pi 2, pi 3, pi 4. It only has pi 1. Okay? So my topology of my manifold comes from pi 1. And pi 1 are represented by closed non-trivial loop. And then my surface, any representative in my surface, is intersecting all non-trivial loop. So if you cut along my surface, you would have to destroy all topology of a manifold. That is called fitting. Okay? So fitting just means destroy all the topology. Okay? And there's a notion called strongly fitting. That means you look at your universal cover, and then take any 2 points at infinity in your universal cover. You draw a geodesic, and then the surface has a cover which separates that 2 points. So this second condition looks very weird, but it's actually very important in geometric group theory. It's related to some big conjectures, virtual properties of 3 manifold, and geometric group theory. So the second notion, strongly fitting, implies the first one. Okay? It just said like my surface somehow in the universal cover linked with every geodesic. So it would imply the first one. I'm gonna show you a picture, so hopefully it makes this more accessible. Okay. All right. So here, my surface may be not totally geodesic, but maybe nearly geodesic. This 1 plus epsilon quasi-Fuchsian is that you look at the limit set, it's a 1 plus epsilon quasi-circle. So in the universal cover, it looks like this. Okay. So this is my H3. This is my universal cover. And then my surface inside my manifold lift to here. Okay. Look at the cover of my surface. So in this case, it's on disk. Okay. Because the surface universal cover is a disk. And then the disk may be sitting in my manifold, not in a perfect way. It's not totally geodesic. It's curvy, right? So it's not an isometric copy of H2, but it's like curvy, where you have some curvature. And then the separation that I mentioned in the last slide means your surface has a cover which separate any pair of 2 points. So, sorry, for any pair of 2 points, your surface has a cover which separate that pair of points. Okay. That's called a boundary separation. So this property will definitely not hold for embedded surfaces, because if your surface is embedded, right? You think about hyperbolic surface, right? If my geodesic is simple closed geodesic, if you cut along simple closed geodesic, you did not destroy all topology, because that geodesic itself is topology. You did not destroy that. Similarly, if you have embedded surfaces, you cut along embedded surfaces, you did not destroy the surface itself, which represents topology. Okay? So you cannot, so fitting surfaces cannot be embedded. All right. And so let me say some very straightforward lemma. So on a hyperbolic surface, how do you minimize the intersection number? Right, take two curves. I can measure the intersection number. This is geometric intersection number. I don't count signs. I just count how many times they intersect. Okay. The way you count this intersection number is that you use this hyperbolic metric. This hyperbolic metric, the curve is going to be homotopic to a unique closed geodesic. Okay? And it's length minimizing. So somehow length minimizing would force us that the intersection number is also minimized. Okay? So this is something on hyperbolic surfaces. You use the metric to help you solve the topological problem. A similar statement would hold for three manifold, but with very strong condition on the surface. So take a closed curve in a pi 1 and take a homotopy class of a total geodesic surface. Okay, so this is geodesic surface. It's not any surface, it's geodesic surface. In this case, you can count the intersection number. And this intersection number is realized exactly by taking the geodesic representative. So you make this minimum, make this minimum. Makes this length minimum, makes this area minimum. Then you realize the intersection number. So this is a very strong condition because in general, your manifold may not have any geodesic surfaces. But what I prove in my paper is that in general, this idea is false. So in general, in three dimensions, right, you have this area and you have this intersection number. One is geometric, one is topological. So what I explain in my paper is that if you minimize the area of your surface, sometimes, so you always have actual intersection with some geodesic. Okay. So in three dimensions, the idea of minimizing measure of the submanifold no longer works so well with minimizing intersection number. You either minimize area or you minimize intersection number, but you cannot do both. Okay? So as a corollary, if my geodesic surface is fitting, it actually transversally intersect every closed geodesic, just like the torus case. Why is that? Because my fitting geodesic surface is going to cut my manifold into components that are contractible, okay, like balls. And then take any geodesic. Okay? You cannot have a geodesic that's supported inside a ball, right? Because a ball has no topology. Ball is contractible. But my closed geodesic is not contractible. The closed geodesic represents pi 1, elements in pi 1. So it's not, so I cannot have my closed geodesic supported entirely in the complement of my fitting geodesic surface. Right? Because otherwise I have a closed geodesic in a ball, and that's actually not possible. Because when you look at the universal cover, so this is H3, this is my manifold. You take any closed geodesic, when you lift the universal cover, it's become unbounded. So if my closed geodesic is supported in a contractible ball, I can lift the whole ball to here. Then in this ball, I found the geodesic that's not possible in the universal cover. Okay? In the universal cover, my geodesics are unbounded. So this means any geodesic would have to intersect my fitting geodesic surface. So it might intersect transversally like this. But it might just walk around the surface for some time and come back to cut it itself. Because if you think about the fitting geodesic on a hyperbolic surface, right, has self-intersection. You walk along your geodesic for some time, and then you have to intersect yourself because you have to destroy yourself to be fitting. Okay? So that's why even if you walk along my geodesic surface for some time, in order to be fitting, you have to come back to cut yourself. Okay? You have to destroy yourself. So that's the lemma. So my first theorem is that take a closed hyperbolic manifold. There exists a constant such that all but finite many total geodesic surfaces are fitting. Okay? So if there exists infinite many of them, then except finite many of them, everything else is fitting. Okay? Moreover, my surface is going to cut my manifold into components that have diameter going to 0. So if you cut along the surface, then the complement shrinks. The maximum diameter goes to 0. So if we compare the statement with the statement for torus, right? Previously, I said random geodesic on my torus is fitting. But in this case, it's replaced by stronger notion of random. It's called all but finitely many. So all but finitely many are fitting. So it's just like this, but stronger. And because of my fitting geodesic surface transversally intersect every closed geodesic, so this property also hold. Okay, so this property also hold, but replaced by the stronger all but finitely many. So all three properties will hold for geodesic surfaces in hyperbolic free manifold. And the reason is I come from the homogeneous dynamics, the Ratner theorem, the rigidity. The rigidity forces your surface to, in this case, equidistribute. Okay, so they cannot miss any geodesic. Take any geodesic, take any sub-segment. If my surface is large enough, it has to come and intersect my geodesic because it's equidistribute. Yes. Yes, because the dynamic system result holds for more general Lie group, not just. Yeah. You mean this result? Yeah. Yes. Because in my paper it's combined with other theorem in three manifold that I don't know how to generalize in high dimension. Yeah. But it holds in every dimension. Okay. Right, that's the first part. So you see that you see the analogy between these two. And the intersection is that you look at the Lie subgroup, look at the orbit, okay? And somehow the orbit exhibits rigidity. And this comes from this polynomial growth of the unipotent subgroup. This is a very beautiful area, beautiful dynamic system. Okay, so now the theorem has an issue, which is that, as I said, most hyperbolic free manifold do not contain geodesic surfaces. So this statement is vacuous. So my next statement would have to use the result of Karl-Marquardt. So Karl-Marquardt, one of their breakthrough is that they solve the surface subgroup conjecture, which has been open for many decades. So in particular, take a closed hyperbolic free manifold. What they can do is that they can construct infinite many 1 plus epsilon quasi-efficient surfaces. So those surfaces are very close to being total geodesic. You look at that paper. The paper is kind of technical. Section 4 is entirely dynamic system. They use geodesic flow. It's a flow different from the flow I use. I use flow cycle flow. This use geodesic flow. And due to the mixing property of geodesic flow, the surface you construct sits everywhere, right? So it's like dense. It's not equidistributed. So there's some interaction between this dynamic system and the homogeneous and the Ratner thing. So here, as a corollary, this is called Bertrand-Weiss boundary criterion. You take any pair of points at the universal cover, just like this. Okay, take any pair of points. There exists a surface constructed by Karl-Marquardt using geodesic flow, such that the surface, so my surface they construct is here, but when you lift the cover, they separate the endpoint. Okay, so you see that this is some uniform distribution property because they are using geodesic flow. Geodesic flow doesn't care about where you start. Okay, you can start anywhere. So you can start, maybe you start here, and you do the pans, and you unwind yourself, you glue many pans, and then you become the surface. Okay? So that's the merit of using dynamic system, where you don't get just one surface. You don't just solve the conjecture. You get infinite many, and they are sitting everywhere. Okay? So this conjecture that they solve is very important because combined with boundary criterion of Bertrand-Weiss and the work of many other people, including Agel and Sagiv and Weiss, so this solves many problems of mini big conjecture like of Thurston's. And here, why do you care about fitting? So look at the statement. The statement is that take any pair of points, there exists surface constructed by Markov which separate that pair of points. Okay? But if you construct a single fitting surface, a single surface separate every pair of points. Okay? A single surface does all the separation. You don't need to change your surface. And we're gonna talk about, maybe we're gonna talk about some merits of this philosophy. Okay? So a single fitting surface does all separation. Okay? That's one application of this fitting geodesic surfaces. And because total geodesic surfaces are rare, and using the idea from Caligari, Marcus Neves, and Karl Smilga, those two papers I spent 9 months reading the two papers, and I benefit quite a lot from reading them. So they combine minimum surface theory with homogeneous dynamics and rigidity. Okay. So this paper I mentioned it because it used Rotterdam theorem and defined this minimum surface entropy, and they give a new proof of mass rigidity. And this paper studied the average measure induced by all of your nearly geodesic surfaces and asked some interesting questions, which help us better understand topology and geometry. So what I prove is that take a closed-up of a manifold. There exists constant. I cannot compute exactly what's the constant, such that every 1 plus epsilon quantitative surfaces is fitting. Okay. So in particular, my theorem tells you there exists infinite many such surfaces because Karl Marquardt, for any epsilon naught, can construct infinite many such surfaces, as in Karl Marquardt's paper, and then those surfaces are all fitting. So this is just tell you the topological property of the Karl Marquardt surfaces. And definitely, in last December, I talked to Marquardt, and he said, after listening to my theorem, what I proved, so I proved the theorem for total geodesic surface first, and then after talking to him, he said, most surface he and Jeremy can't construct should be fitting. So that's why in the end I proved this theorem. Gratitude to him. All right. So here, the way to interpret this theorem is that the surfaces have really small curvature, but somehow so if you think about your surface, they have small curvature, but somehow they have to sit everywhere. Okay, they have to go through, they have to, you cannot have a small curvature surface that's concentrated on a small region. You have to go everywhere. Okay, because I'm using my Rotterdam theorem to push my surface to everywhere. All right, some corollary. Corollary is that if you consider the collection of all embedded surfaces, okay, incompressible embedded surfaces, then except for finitely many of them, everything else is curvy. Because everything else has this quasi-Fuchsian constant larger than 1 plus epsilon 0. Okay. So this is very different from 2 dimension. Because in 2 dimension, what is the embedded geodesic? Well, these are simple closed geodesic. Which one? This one? Is fitting. What do you mean by not fitting? Yeah, but I said larger than 0. So total. So okay, there are 2 collections. Total geodesic will be correspond to epsilon equals 0. Those are all but finite many of them fitting. Okay, that's one collection. And everything else, those are nearly geodesic but not total geodesic one. Everything else is fitting below this range. Yeah. Yeah. Okay. Right. Okay. So a corollary is that usually topologists consider embedded surfaces. Okay, they do surgery, they cut and paste. But those embedded surfaces they consider, except for finitely many of them, are all curvy. Okay, they are not total geodesic. Okay. So this is very different from 2 dimension. 2 dimension, you can easily construct infinite many simple closed geodesic. Okay, they are embedded and they are geodesic. Okay, it's very easy. Infinite many of them. But in 3 dimension, what I tell you is that whenever you take infinite many embedded surfaces, okay, eventually they are all like curvy. They're not geodesic. They're curvy because this one gives you low bound on curvature. Okay, so I'm gonna give some more application. So actually, fitting is actually intersection of quite different fields. Any questions? Yeah, rigidity. Yeah, because I use Ratan theorem. Because in high dimension, we don't know whether they exist codimension one nearly geodesic submanifold. If they exist, they should also have this fitting thing eventually. But Karman-Kochi result only work for 3 manifold. Yeah, because like in hyperbolic 4 manifold, I'm not sure whether there's a way to construct those. If you look at the paper, then the way a dynamic system works every dimension, right? Mixing ray of geodesic flow, so something works in every dimension from his paper. But how do you construct those surfaces? You need to use a frame, and then you construct like triangle and pans, and then you glue pans, right? But those are much harder if you want to construct 3 manifold by hand. You see what I mean? Like from yeah. Okay. All right. Yeah, that's the virtual Hawking thing, right? It's, yeah, so take any surface, take any immersed surface. There exists a finite cover, so that surface becomes embedded, but not every one of them. Yeah. And virtual Hawking is also solved by Ego, but also use Karman-Kochi. All right. So that's one application to topology. And then maybe you like minimal surfaces better. So translating into minimal surfaces, this set take an embedded minimal surface. Okay? Either it's total geodesic and of genus less than G naught. That's the answer for my first theorem. Or it has curvature larger than this constant. So this is telling you it's curvy. Okay, so you have a gap theorem for minimal surface. Okay, if you like differential geometry, this is something I phrase in terms of differential geometry. Maybe you like geometric group theory. Okay? So this also has application to geometric group theory. This existence of fitting surfaces answers a question asked by geometric group theorists about cubulations. So recently, in the last decade, there's a trend in math which studies the space of something, okay? Like the space of minimal surface, the space of curve. And so you don't like a single object. You look at the collection of objects, and you want to say some properties of this collection. Okay? And then geometric group theorists of Fioravanti and Hawking, they are studying the space of cubulation for those Gromov hyperbolic groups. So I don't have time to define the terminology. But what I can tell you is that if your hyperbolic group acts on a cat-zero cube complex, so a cube complex is a high-dimensional generalization of trees. It's basically, you can think of like a cube complex. I take a cube, and then you glue this, you glue a square with a cube, but with some isometry. So if your group acts properly and co-compacting on a cube, has a cube class, you get many good property of your group. So this is, they study that they want to understand when your group acts on the cube complex and with some good actions. Okay, so cubulation with single hyperplane and some cubulation. So that's some terminology going on here. And a corollary of my result is that I can give you, okay, I can give you, take this fitting surface, a single fitting surface give you one cubulation. Moreover, it has this one orbital hyperplane property. Moreover, it's hyperplane essential. So I can have those nice things, like they're together, and moreover, it has hyperplane stabilizer is a surface subgroup, so it's very concrete. So here it's just existence. You don't know what the hyperplane stabilizer are. Okay. So it's a very interesting journey. So because I learned geometric group theory last month, okay. And then I talked to this one, and then we realized that he's using combinatorics to prove something, and I'm using Rothnard theorem dynamic system to prove something, and they will intersect. We intersect at this theorem here. So there's some philosophy in math where you can do both. You can prove either using combinatorics or use homogeneous dynamics. So I really love this journey, and this is great. This is very interesting to me. But I can tell you, so there are papers coming from combinatorics, and they works for every Gromov hyperbolic group. Okay, so it's much more general than my group. With my group, are the fundamental group of closed hyperplane manifold or the closed arithmetic manifold. Okay, so my result, which works in a much narrower setting, the result is much more general but weaker because it cannot do both. I can do both and with something else, and I can tell you this rigidity. Rigidity tell you that you take this hyperplane. So take this hyperplane, right, and then you do arbitrarily small deformation of your hyperplane. You're gonna get a fitting surface. There's a fitting surface sitting in an arbitrarily small neighborhood of this guy. Okay. So this statement appear in both my paper and in their paper. So this is why we intersect. All right. Like how much? All right. I also do the other direction where if your three manifold, geometric three manifold is a Riemannian three manifold supporting one of the model geometry. If your geometric three manifold supports a pi bar injective fitting surface, what does the manifold look like? So I classify all of them. It's Euclidean, spherical, and H times R, and hyperbolic. So this part I also very enjoy because it's my first time doing non-hyperbolic geometry. Previously, I thought only hyperbolic manifold are rich and in three-dimensional, okay, not in four-dimensional. Hyperbolic manifold are very rich and very complicated. I think only hyperbolic three manifold can support fitting surfaces, and then Nathan Dunfield, he using some programming, he can show this fitting surface in Euclidean manifold. So I start to think about how to classify all those geometry. All right, that's some classification. And I want to tell you that this frame bundle, so even if you only care about topology, why do you want to understand frame bundle? I'm going to give you two examples, one from Margulis and one from my paper, and also paper of Benloy and Fernando Arasa. So the Grassmannian bundle is a two-plane bundle over the manifold. So my manifold is three-dimensional, and my Grassmannian bundle is five-dimensional. Okay. So usually the dynamic system happens in the bundle, right? So this is my Grassmannian bundle, this is my manifold. So this is five-dimensional, this is three-dimensional. Okay. Topology usually happens here. Dynamic system usually happens here because you want to have some flow and something. And here, the projection, you can make this projection Riemannian submersion. Okay, this three property also appear in the paper of Karl Markovic Smilga. So the projection is Riemannian submersion, and then so it's a nice metric. So just think you have a nice metric here, and you put back to the metric here. But the metric here, because my Grassmannian bundle is a point and a tangent two-plane. So the metric here not only measure the distance between the points, but also measure the angle. Okay? So it has two more dimensions coming from the angle. Okay? So the metric here is more subtle. Okay, so let's say I only care about topology. Why do I want to understand the Grassmannian bundle? So there was this problem that Margulis did 40 years ago, which count the growth rate of totally geodesic surfaces. They want to understand, like, if you list total geodesic surfaces, those are geodesic surfaces, okay? Geodesic surfaces in your three manifold, what is the growth rate, okay, with respect to area? That's a natural problem. It's actually a natural topological problem, okay? So what Margulis did is he counts surfaces here. Why do you want to do that? Because your surface might self-intersect, okay? They might self-intersect because I proved there's a fitting because they must intersect. And take two surfaces, they might intersect, okay? So in a three-dimensional space, your surface is intersecting. But if you leave to the Grassmannian bundle, they all become embedded and disjoint. And then you use pigeonhole principle. So it's much easier to count things. So because here, my surfaces are disjoint and embedded. So it's much easier to count them, right? Because you can do like this volume, whatever, to count the surfaces if they are disjoint and embedded. Okay. So basically, the idea is that in three-dimensional space, you have the shadow, right? Like this two does not intersect. But you project to two-dimensional space, they intersect. Okay? So my surfaces in here after lifting to the corresponding bundle, become embedded and disjoint. So it's much easier to count them. And also, my paper used the corresponding bundle to give a homotopy problem. So basically, it's very interesting. So basically, what happens is that inside your manifold, inside your surface, right, you might have a geodesic. You might have a curve that is also very close to this geodesic. Right? You can converge to this geodesic in the house of sense. The house of distance can go to 0. Okay, in the end. But they are not homotopic. Right? Because this red geodesic, you put it tight, it becomes far. So closeness in the manifold level does not give you homotopy. But closeness here indeed give you homotopy. So in a 5-dimensional Grassmannian bundle, if you are very close to a total geodesic surface, it must be homotopic to total geodesic surfaces. That is why you get stronger topological control if you pass the cover. Okay. All right. So here I want to state one more thing I learned from Markovich, which is that so asymptotic Fuchsian means my surfaces are becoming more and more total geodesic. Okay. So surfaces constructed by Karl Markovich, they cannot be total geodesic, okay, because your manifold may not have total geodesic surfaces, but they can be nearly geodesic, and they can be as small curvature as small curvature as possible. Okay, it might make epsilon not go to 0. So what I prove in my paper is that take a sequence of such surfaces that are non-commensurable. Okay, they're not covering each other. Then, in the end, it must be dense. So the picture is that locally, okay, this is my surface. Locally, my surfaces are becoming geodesic. So locally, the curvature becoming small and going to 0. So locally, my surface is becoming nicer. But globally, because of Ratner theorem rigidity, they are going everywhere. This is very different from 2 dimension. So this tells you there's a dichotomy between geometric complexity and topological complexity. Right? So make my surface small curvature, so geometrically they look better. Topologically, they are becoming dense in the Grassmannian bundle. So Fernando Ars and Benloy, their paper also works on finite volume, so stronger. And also, but so it's unfortunate we overlap at the theorem. But we have very different motivation. I care about topology, but they care about geometric analysis and this rigidity question. So we will have some friendly conversation. And how about measure? Measure is the opposite. So Hausdorff limit is always dense, but measure limit is every convex combination of my ergodic measure. So if my manifold has 2 total geodesic surfaces like this, then this paper can make sure your surface converge to maybe point A of this measure plus point 2 of this measure. So measure is everything. Right? Every convex combination of my ergodic measure. But Hausdorff limit is always dense. That's very different from 2 dimension, because as I explained, in 2 dimension, right, I can have my measure supported on 2 blue curve, like 20% here, 80% here. And then the Hausdorff limit, you just join them by geodesic. But this is not dense. This Hausdorff limit is not dense, but here Hausdorff limit is always dense. That's the difference. So basically, in 2 dimension, I want to join 2 geodesic. I can just draw a lamination and join them and make this thing connected. In 3 dimension, you take 2 surfaces, you want to connect them, you have to go through a dense set. That comes from I used Ratner theorem. Okay. All right, almost time. And here's a picture that this is my minimum surface area minimizing, so it's least area in my homotopy class, but it has actual intersection with this geodesic, because you see that I can perturb my geodesic or perturb my surface so that these two intersections are removed. It just make my surface go higher. Then these 2 geodesic, these 2 intersections will be removed. Okay. All right, so that's why in 3 dimension, minimizing area doesn't minimizing intersection number. Okay. To summarize, my paper is about some analogy and contrast for the submanifold theory of hyperbolic surfaces and hyperbolic field manifold. So the first property is that like minimizing area, minimizing measure, minimizing intersection number. But this is true in 2 dimensions, but false in higher dimension. Okay? And fitting geodesics have some transverse intersection with every geodesic, but this is true in every dimension because that just relies on the local picture of geodesic and geodesic manifold. Random geodesic hypersurfaces are fitting. Hypersurfaces are codimension-wise surfaces. Well, this is partial result in 2 dimensions, and I say my result sets all but infinite many are fitting. And the last property is that there exists infinite many embedded geodesic manifold. This is true in 2 dimensions, but false in higher dimension. They have a gap. It cannot be nearly geodesic. And last one is that the Hausdorff limit is different from the measure limit. This is true in 2 dimension and high dimension, but they are different because in 2 dimension, the difference comes from this lamination, which is geodesic. In high dimension, it comes from the dense set. Okay, I would like to stop. Thank you very much.
Thanks, speaker. So, any questions?
Yes. Okay. Uh-huh. Okay. Okay. Let's see. Okay, yeah. So here I consider the equivalence class modeled by commensurable. That's already like projectivizing because I consider a surface and cover to be equivalent. So, and here I don't know whether you're gonna get a ball or something because they, yeah, that's a very good question. I'm considering the space of all surfaces, yeah. But I can only prove some property hold for surfaces that are near that line. So I don't know what else. The rest of the surface, I'm not able to say something about them. So, but that, thank you. That's a very interesting question. Yeah. Right. You're right. Okay, that's great. That's a great question. Okay, thank you. Yeah.
So any questions? Yeah. Okay, no question. Let's thanks Professor Xiaolong Han for that talk.
Okay, thank you.